All right, today we're jumping into two of the biggest questions you could possibly ask. First, how will the entire universe end? And second, what is reality really? And what's wild is, it turns out you might not be able to answer one of those without answering the other. So let's just start with the biggest question there is. We're not talking about the future of our planet or even our species. We're talking about the final fate of the entire cosmos. What's the end game for everything we see and everything we know? For the longest time, physicists had a pretty straightforward, if kind of depressing answer. It's a prediction that comes straight from the laws of heat and energy, a kind of cosmic expiration date, if you will. And that final state is called the heat death. Now, when you hear that, don't picture some fiery apocalypse. It's actually the exact opposite. It's the universe reaching a state of perfect, boring equilibrium. All the energy gets so evenly spread out that, well, nothing can happen anymore. No stars can burn, no life can exist, no work can be done. Just a final, absolute quiet. This whole idea actually goes way, way back to the 1850s to a physicist named Lord Kelvin. He was thinking about this fundamental rule of nature called the second law of thermodynamics. You can basically think of it as the your room always gets messier law. Disorder or entropy always tends to increase. So Lord Kelvin just asked a huge question. What if you apply that simple rule to the entire universe? So what does this look like? Well, it's not some big, sudden explosion. Think of it more like an incredibly long, slow, cosmic fade to black. Let's just walk through the predicted timeline. Right now, we're basically in the universe's vibrant childhood, full of bright stars and bustling galaxies. But this doesn't last. In this scenario, star formation eventually just stops. Then, over timescales that are almost impossible to wrap your head around, the galaxies themselves dissolve. Black holes become the rulers of the cosmos until even they fade away, evaporating over googles and googles of years. And in the very end, all that's left is a cold, thin soup of particles drifting in the dark, a universe at absolute rest. Okay, so that's the classical prediction. It's a simple, elegant, and really, really bleak story. Case closed, right? Well, not so fast. Because there's this little thing called quantum mechanics that throws a massive wrench in the works and opens up a profound puzzle about what reality even is. This really gets to the core of how bizarre modern physics is. See, on one hand, quantum mechanics says that when we're not looking, a particle exists in this ghostly blend of every possibility all at once. But then, the instant we measure it, bam! Reality seems to just roll the dice and snap to one single definite outcome. Two completely different sets of rules. To make this a bit more real, let's forget about galaxies for a second and think about something tiny, like a single ammonia molecule. You've got this nitrogen atom that can be in one of two positions. We can just call them up or down. Seems pretty straightforward. But here's the quantum twist. Until you actually check, the atom isn't up and it isn't down. It's somehow both at the exact same time. It's in this weird state called a superposition, and it's our act of looking that seems to force it to pick a side. This whole mess is what physicists call the measurement problem, and it boils down to three huge questions. 1, how do we get from that fuzzy, maybe world of quantum mechanics to the solid, this is here world we all live in? 2, why do we only ever see it as up or down and never that weird both at once state? And 3, if the math says multiple outcomes are possible, why do we only see one? What decides? Since nobody has a single, definitive answer to those questions, physicists have come up with a few different and competing stories to try and explain what's really going on behind the curtain when we're not looking. Let's break down the big three. First, you've got the many worlds idea. This one's wild. It says every possible outcome actually happens, each in its own separate branching universe. Then there's objective collapse, which suggests the collapse is a real physical thing that happens all on its own, no observer needed. And finally, you have epistemic views, which basically say we're all overthinking it. The math isn't describing reality, it's only describing our knowledge about reality. So let's dive into that first one. In the many worlds picture, the moment you measure that ammonia molecule, the entire universe splits. In one new universe, you see up, and in another, a parallel version of you sees down. Both are equally real.
Objective collapse theories, on the other hand, are a bit more grounded. They say, forget about observers. The collapse is just a law of nature. Some brilliant physicists like Roger Penrose have even suggested that gravity itself might be the thing that's forcing reality to make a choice and snap out of that fuzzy quantum state.
And then there's the epistemic approach. For them, the whole measurement problem just kind of dissolves because the wave function was never a real thing in the first place. It's just a mathematical tool that represents our personal knowledge. So when we measure something, we're not collapsing reality, we're just updating what we know. So, why don't we just dive so deep down that quantum rabbit hole? What on earth does any of this have to do with the end of the universe? Well, it turns out it's everything, because the story of reality we choose completely changes the final chapter of the cosmos. And this is really the key takeaway here. That neat, tidy story of heat death we started with, it might be totally and completely wrong. The ultimate fate of everything seems to hang on the true nature of quantum reality.
Take gravity, for instance. Physicists like Lee Smolin argue that gravity is an anti-entropy force. It does the exact opposite of what the heat death theory predicts. It doesn't spread things out, it pulls them together, creating complex, amazing structures like stars and galaxies. So in this view, maybe the universe isn't programmed to run down. Maybe it's built to create complexity.
And here is where it gets truly, truly mind-bending. Even in that unimaginable cold and dark of a heat-dead universe, quantum mechanics might allow for the ultimate fluke, a random quantum fluctuation, something so incredibly rare that it could spontaneously reverse all that decay and essentially reboot the entire cosmos, sparking a whole new Big Bang. So how long would you have to wait for an event like that? Well, some theories predict a timescale of roughly 10 to the power of 10 to the power of 10 to the power of 56 years. I mean, that's not even a number you can properly write down or think about. It's so fantastically large, it's basically forever. But, crucially, it's not technically infinite. And the implication of that is just staggering. It means our universe might not be a one-shot deal, a clock just winding down to a final stop. It could be just one chapter in an endless book, part of a cosmic cycle of death and rebirth that stretches across an eternity. And that leaves us with this final, profound question to think about. Is our cosmos a single finite story, destined to end in a big chill? Or is reality something much stranger, an endless book where the final page is also the very first? The answer for now is still out there, hidden somewhere in that beautiful quantum fuzz.